Good afternoon. I'm Jason Thomas, project engineer at America Makes, and I'll be your host for today's America Makes TRX webinar series. Just a little background on the TRX webinar series before I introduce our speaker. As America Makes continues its mission to expand and accelerate the footprint of additive manufacturing and 3D printing, this medium called the America Makes Technical Review and Exchange webinar series was created. By creating this platform, it allows the additive manufacturing and 3D printing community to come together and share knowledge and experience with a broader community. If you or your team are interested in presenting during the TRX webinar series, there will be a link to complete the request form at the end of our series today, or you can contact the America Makes TRX webinar series administrator, Jason Thomas, directly. A few important notes before we kick off today's series. At the end of the presentation, there will be an opportunity for a brief question and answer. If during the presentation you have a question, please go ahead and submit it in the Q&A space on your WebEx screen, and I will ask it during the Q&A session. I'll do my best to get all of your answers or all of your questions answered today. Today's webinar is going to be on AFX in practice, from cubes to real parts. Without further ado, it is my pleasure to introduce Cesar Terrazas from Aconity. Cesar is Aconity's managing director. Cesar, I'll go ahead and let you introduce yourself and get the presentation started.
Right, excellent. Thank you so much, Jason. And good morning to some of you guys. Good afternoon to some others. Thank you for the kind introduction, Jason. And yes, so the topic of today's presentation is the AFX in practice, from cubes to real parts, by AconityUS, which is a distributor for Aconity 3D in Germany. I'll go a little bit more into the details of the Aconity 3D systems, Aconity 3D, excuse me, philosophy when it comes to the machines and the systems that we offer, right? And as Jason introduced me, so my name is Cesar Terrazas. I've been managing director for AconityUS since basically December of 2021. And today we're going to be exploring the AFX laser, which is one of the offerings we have for one of our systems. It's one of the lasers that is employed, and one of the latest additions that we have to our systems, providing a lot of alternatives, not only for research, but also for production of components. This talk is going to be specifically related to the processing of Inconel 718, right? And we'll hope it's going to be of your interest. So Aconity 3D, what we do, basically we want to provide solutions for the different customers out there that are looking at additive manufacturing using specifically laser particle fusion and also directed energy deposition systems. So we provide mostly equipment. We also provide job shop capabilities, testing capabilities, material distribution, and consulting. All of these, both in locations in Germany, which is in Aachen, which is the place for Aconity 3D, and then also here in El Paso, Texas, which is the headquarters for AconityUS. So in essence, we want to be the one-stop shopping for customers, again, doing either production or research into additive manufacturing using laser particle fusion. So this slide captures kind of the ethos, right? The philosophy that Aconity 3D has, where our systems can be configured depending on the needs of the customer. So what you see here in the middle of the slide is one of our systems, and then around it you can see the different modules that can be attached as per the customer requirements. Right? So we have preheating capabilities that go all the way from 500 degrees C to 1200 degrees C. Right? We have different lasers that can be attached to our systems, different monitoring options, and then you can also purchase extra modules, let's say separate chambers that can be used for improving productivity and processing times. All of these while having Aconity Studio, which is the internal solution that we have for controlling every single one of the modules that are attached to our systems. Right. Now, when it comes to the talk of today's topic, right, so we are going to be talking about the AFX laser and processing. So we know that laser particle fusion is a very complex process, right? It entails the application of an ignition source, which in this case is a laser, right, to melt materials. And we know most people that are attending this webinar are probably familiar with the fact that this is a very complex process with multiple phenomena that are occurring because of the interaction of this heat source with the melt pool, right? So during that interaction, I mean, you see multiple phenomena that include a temperature field or temperature gradient. You see absorption of the energy from the laser, phase changes. The melt pool is being affected, and all these things that are contributing in the end to the finished part. Now, the interaction time for a lot of these is very short-lived, but nonetheless has a tremendous impact into the properties that are producing the resulting part, right? So again, we have many influencing factors, but a lot of them are not necessarily very well understood. And as we will see today with this presentation, the AFX has a tremendous impact into the microstructure and the resultant mechanical properties of the components. So what is the AFX laser? So the AFX laser is the offering from Enlight, which is a 1.2 kilowatt laser that can be used for obviously melting in laser powder bed fusion. But the main characteristic of this laser is that it can be tuned or it can be changed to the emission mode in 7 different modes, right? So we can go all the way from the regular Gaussian beam, which is the mode 0, towards the left, the image on the left. And roughly we have a beam diameter that is anywhere from 80 to 130 microns. But then we can explore different emission modes all the way to a full ring mode or ring beam, right, which can be 360 microns in diameter. Now, it's very interesting that because of this offering, now we're opening the door not only to doing very fine structures, with using the smallest beam that can be attained, right, for something like very fine resolution, very fine components. We can also do optimization, right, whenever we want to do components that maybe have a mixture of bulk properties along with very fine details. And then in the end, we can also extend to the productivity by going and melting at a higher rate, as will be demonstrated with some of the results in this presentation. Now, also interesting to mention is that through Aconity Studio, we can basically flip through any of these modes of emission almost in millisecond scale. So that means that within a single vector that is scanned, you can modify the emission mode, altering the characteristics of that beam and altering the effect that is going to be seen by the powder. So in a nutshell, what this study is going to cover is basically we're going to provide you with the experimental setup at the beginning. What is it that Aconity 3D did when it comes to the study, how it was set up in the machine that was employed, and then details are going to be presented as far as the processing parameters. And then in the middle, which is the bulk section of the mechanical properties that were obtained by means of this experimental study. And then towards the end, we go through a rationale and some of the investigations that were done to evaluate why, the results of the mechanical properties that were obtained. So going directly into that parameter study, the experimental setup employed the Aconity 1 squared, which is the legacy system in Germany, basically the second iteration of the Aconity 1, which was the first production machine that was commercialized by Aconity. In this particular case, you see the layout of the components that were built, all of them using Inconel 718 as the material. And then essentially there were 6 runs, in total 180 samples that were small cubes used for assessment of the microstructure. And then also we built coupons that were suitable for extracting tensile specimens for characterizing the tensile properties out of specific parameters. You can see that the matrix of the different parameters that were tried for power, anywhere from 200 to 1,000 watts, scan speed of 100 to 2,000 millimeters per second, different hatching distances and layer thicknesses of 50 and 100 microns. But the most important parameter that we were interested in studying was really the ability of the emission mode to change those characteristics. So that's why you see in the bottom, we have 3 indexes that were tried, right? The first one, index 0, in a defocus mode, which essentially causes a Gaussian beam, which is slightly defocused. to match the diameters of the index 3 and index 6 emission modes. All right. So the first thing that the team noticed when they did this research is that for a layer thickness of 50 microns, right, and again, using, just comparing, for instance, as you see in the slides, index 0 in the left and index 6 in the right. So you can see that the process stability gets really there. There's a lot of processing parameters that can be used, right, and essentially result in densities in excess of 99.5%. One thing to notice is that also with the index 6, we see theoretical build rates of up to 54 cubic centimeters per hour. So this is just a glimpse of the increase in productivity that can be expected, right? Also notice that just by changing the emission and defocusing the laser, which is fully available not only for this laser but other lasers that we offer to our 3D scanning technology, we can stabilize that process parameter space a lot. Right? So the same thing happens when you go to layer thicknesses of 100 microns, right? A little bit reduced compared to the 50 microns, but still, there's a bunch of parameters. Let's say, power of 500 versus speeds of 600 that still result in densities in excess of 99.5%. And the same goes for index 6 at this layer thickness, right? So you can see that even though more widespread, the parameter space is also widened, right? Meaning there's a lot of parameters that are going to result in almost fully dense components. The interesting part is that once the components are produced, right, and if you assess the mechanical properties normally measured for the yield strength, elongation, and then the tensile strength, or the UTS, what you see in the as-built condition is that very comparable results, which are to be expected just because you're using a beam that has similar diameter, regardless of the mode. Right? So we see yield strength in the range from 562 to 577, not much difference. But then really when there's a difference, it's in the elongation at break. In here, just by tailoring the mode, so that means that we are getting increases of up to 12 to 11% higher strain or higher elongation of break. Now, if the team went ahead and actually did a heat treatment of the component, which is on pair with the ASTM standards, and assess the yield strength again, right, of these components, and you see again the same trend. Even though reduced, you see an increase in the yield strength just because it's expected after the annealing and solutionizing heat treatment that was performed. But then the elongation of break, even though it is reduced slightly, you still see an increase just by switching to the operation mode on modes 3 and 6. Again, we're seeing a consistent trend, which is in emission mode number 0 or mode 0 versus emission mode number 6, you see up to 12% increase in elongation of break. Now, it's important to also do the characterization of the mechanical properties at elevated temperatures, given that Inconel 718 is to be subjected to these operating conditions, right? So it is this particular temperature, 650, is of importance for understanding the creep properties and just really the operability of the alloy at these high temperatures. Again, you see the same trend. After assessing the yield strength of the material, we keep very consistent properties, right? They don't vary that much depending on the emission mode. But then when it comes to the elongation at break, in here we still see an increase in elongation at break, just because of the emission mode that is using the laser. So this is just assessing again the mechanical properties depending on the orientation. We see the same trend. This is just providing an overview of tensile produced at 0 degrees, 45 degrees, and 90 degrees. And in here we see the same trend, right? Very consistent mechanical properties. This is just in the as-built condition, not necessarily with any heat treatments. And then if you look at the right side, so that chart indicates also, increases that go anywhere from like 6% up to 11%, 12%. elongation of break just because of the difference in the emission mode. So again, the strengths are very comparable, but the elongation of break really increases. Now, at this point, the team, decided to see what was the rationale behind, this kind of behavior, since even, sustaining a heat treatment at elevated temperatures and testing at elevated temperatures did result in consistent mechanical properties, a consistent behavior, right? So there was a need to explain that kind of behavior on the results obtained. So the very first thing that they tried was basically your regular microstructural analysis, doing an optical microscopy assessment, as you can see in these micrographs, depending on the emission mode. And then you can see different magnifications for the micrographs obtained for the material. And in here, there's not much difference when it comes to the melt pool dimensions and melt pool characteristics, right? Very similar, although as you will see later on, the melt pools that are generated by emissions mode 3 and 6 are shallower and smaller, like flatter compared to the regular melt pool that you see normally in these processes. The second thing that was evaluated was using SEM and looking at one of the features of Inconel 718, right, which indicates the degree of strength that it's going to have. It's also assessed from the primary dendrite arm spacing, which is one of the solidification features of this material, and also the segregation behavior for molybdenum, titanium, niobium, and carbon. When it comes to the primary dendrite arm spacing, you can see, again, very consistent, not very influenced by the emission mode. So that meant that there's going to be something else that is really causing this behavior. Continuing with the SEM observations, in here we see, for instance, the SEM of the defocus versus index 6. Index 0 and index 6 essentially exhibit the same behavior. The dendrites don't change substantially. The precipitation of carbides and other phases that are developing in this alloy also very similar, right? They don't change much. So there needed to be something else that might provide an explanation as to why the behavior was observed as it was for these results. So when the team started looking at the edge micrographs in the XY plane for some of these components, that's when they realized maybe the first clue as to what was providing this kind of behavior. And if you look at this, for instance, this microstructure that developed right here, right, you see that the grains have some directionality to them, right? You see the grain boundaries, you see a lot of grains that are growing in the preferential build direction, but then there's others that are competing in different directions, right? And this is for emission mode 0, right, which is again the regular Gaussian beam. If we compare versus the ring beam, now we see mostly cells, which is indicative of a behavior in which most of the grains are actually oriented or growing in the build direction, in the build plane. And indeed, after an assessment was made into the microstructure through electron backscatter diffraction, you can see that indeed the texture of the component changes because of that directionality of growth, right? So what you see on the left side is that for index 0, defocus mode, again, you see the characteristic behavior that is going to be observed for the microstructure, where you see random crystals aligning in different directions. And then versus index 6, where you see almost a single color, meaning a lot of the grains are just growing in a particular direction, approximating, perhaps single crystal growth. So a lot of epitaxis happening, which leads to that characteristic texture that you see in these maps. So again, that preferential orientation growth for this alloy, right, in the 0, 0, 1 plane, it's explained by these EBSD results, right? So it's a very sharp texture that is created just by the emission in the ring beam versus the regular Gauss beam. When it comes to the explanation as to why this behavior develops, the team looked back at the micrographs exhibiting the features of the melt pools, right? And what is evaluated here is okay, how shallow or how big the melt pool might be. Normally, you see these melt pools that are like a half moon, right, as you see on index 0. And the dendrites usually are going to grow 90 degrees to the boundary of that melt pool, essentially following the thermal gradient, right? So the most energy is being deposited in the center, so you will see the grain, not the grain, the dendrites actually growing towards that direction. But because of that curvature that you see in the regular melt pool, there's going to be opportunities for grains to, or dendrites to grow in different directions, and eventually the grains as well. But when they look at the index 3 and index 6, again, the ring beam causes these shallower melt pools that are smaller, right? So they have an aspect ratio that is different. And that causes, sort of like a more planar front, which doesn't allow for other directions other than, the primary build direction to develop. So again, the comparative growth that you see with the index 0 is kind of reduced in index 3 and 6, right? And that leads to the directionality and the texture that is observed. Not only does this open opportunities for exploring, the directional growth that it's traditional in, aerospace components like turbine blades, but also, approximating the behavior of single crystal behavior. And indeed, when you look again at the heat-treated conditions, for yield and tensile strength, this is an overview, right? So you see the trend very clearly. The mechanical properties are not affected as much, but indeed the elongation of break, which is a feature.
Caesar there. Just give him another second here to rejoin us.
Oh, can you hear me now?
Yeah, there he is. All right, Caesar. We got
Sorry
you back.
about that. Okay, apologies for that. Yeah, I don't know how much was missed out of what I was saying, but I'll resume with this slide. Again, I was mentioning that the mechanical properties, yield and tensile strength are very consistent, independent of the direction of testing, and independent of the emission mode of the laser. But really, the elongation of break is what exhibits that feature. And it is explained because of the directionality or the texture that is influenced by the emission mode. Same thing for the heat-treated condition. Again, we see a very clear trend, right? Even though high testing temperature reduces the strength, which is expected, right? But the behavior or the elongation of break, right, it's still maintained. So this is a summary again, where we try to capture, okay, the directionality of growth that's influenced by the emission mode of the laser is what's really providing you with this similar behavior in strength, but different behavior in elongation of break. Right. Now, when it comes to actually making a useful case, for this kind of technology, so the team decided to test this in a component that is more suitable, right, for an actual application. So they decided to construct this turbine blade geometry, with sections that were constructed using the different emission mode. So again, they started with the emission mode 0, and then there was a middle section with emission mode 3, and then finalizing with emission mode 6, which is the full ring. They did cut-ups, right, and indeed, you see the behavior that was explained before. You still have directionality of growth towards, the higher emission modes, mode 6 and 3, and then more of an equiax behavior in the mode 0. So again, the main thing to capture from this slide is that not only is for cubes, right? It's not only on the tensile specimens, which has been kind of like the limitation of most research studies. They demonstrate in small components or maybe tensile specimens, but they don't demonstrate into an actual component. So with this kind of blade, right, you can demonstrate that it's the effect can be controlled at different parts within a given component, right, and not only parts that are very small, not only cubes. So the grain analysis for this kind of component actually confirms also the results of EBSD. Again, bear in mind how this experiment was performed. So you started a component that was initially with the Gauss beam emission, and then it transitioned into the ring beam. So you see Obviously, there's an area of the grains that increases because, again, the grains are becoming larger, right? The aspect ratio is also changing. And then the number of grains is getting reduced, right? From the Gauss beam, you will expect to see more grains because you have an equiax structure, and then they start to reduce towards the emission mode in ring beam, again, just because there's more grains that are being epitaxially grown and basically sharing a common feature. So the team decided to push a little bit forward with doing an assessment of how this will impact, right, the productivity in an actual application for production, right? So if we look at a single blade, okay, that's good. That's a good for an experimental case, maybe validating some of the results. But then what are the improvements that are going to be brought by just going with some of these technology advancements in the laser emission modes, right? So in here you can see basically 9 of those blades within the envelope of an Aconity MIDI Plus, single laser, right? And in this case, it's obviously going to be the AFX laser. We have 9 parts and a total part volume of 58 cubic centimeters. Right? So doing the analysis for this kind of behavior and comparing emission modes, right, we can see that the time distribution, for instance, we see a huge effect in the exposure time just by going with the AFX laser, right? And bear in mind that for the standard configuration, we have something like 40 microns in layer thickness, 80 microns in hatchet space, and then a scanning velocity of 1,000 millimeters per second. If we transition into the AFX 50, meaning mode 3 or mode 6, AFX 100, so we can see how they double, right, the layer thickness. Hatching parameters also got kind of double, and then increased speeds just because of the increased stability from using this type of laser. Now, having in mind that your time constants are going to be like the machine preparation, part extraction, and inertization, you can see the effect that that's going to have on the pie charts, as far as the distribution of time allocation. So you see that in the standard operation, the exposure is close to 84% of the time invested, right? So that's a lot of exposure time. But then when you go to the AFX 50, it drops to 68%, and then even further to 51% of the time for the AFX 100. So you can see some of the numbers that the team calculated, starting with 70 hours as the baseline with the standard laser, right? Or not the standard laser, the standard AFX laser in emission mode 0 versus emission mode 3, 30 hours, emission mode 6, 13 hours. So in theory, it is possible to reduce the time up to 80% because there's still other things that can be optimized, now that the exposure time has been also optimized. So this is when it comes to the time distribution. What happens when we're talking about the cost, right? Which is one of the, if not the most important question. Right? So the cost distribution that they did, again, an analysis taking into account some of the constants, for like the personal cost for like preparation of the machine hour time, which is calculated also as a standard, right? And then the cost of the powder. So fixing those variables, and again, analyzing just the cost that is going to come from either the build, the part, and the volume from the different emission modes. And again, you see a very significant trend. Again, the exposure time is taking 78%. If we go to the AFX 50, that's 63, and then 34% of exposure. So that means that you are able to optimize basically 45 to 75% of the baseline, which is the standard operating mode. And again, bear in mind that now that you know these numbers, as an institution, you can play with, okay, what are the preparation, what is the inertization cost, maybe looking at suppliers that are going to provide your processing gases at a cheaper price. So there's still ways to even optimize even more, the cost distribution for this. So in conclusion, in an outlook for this presentation, we talked about the process stability that is brought in, by just using the AFX laser, which is multi-emission mode laser offered by Aconity 3D. In this case, the less overheating and the ring beam processing allows for more stability, which translates into what we saw in the results for microstructure, right? Your shallower melt pools, also opening the parameter space and essentially creating this texture that is to the benefit, in this case, of the mechanical properties, right? So there's even more possibilities to explore these. Again, only 3 of the 7 modes are being described in this work, but there's an opportunity to explore even more things, right, with this kind of emission lasers. And it goes in line with some of the offerings that Aconity has as well, like the ability to process data from acquire in situ from the 3D scanning device, which leads to high resolution visualization of the data when it comes to the emission. Some of the things that we offer that include the high-speed camera for looking at the melt pool deposition and characteristics, right? But the main part is really the productivity. Now that we know that it's possible to kind of amplify, right, the production space while reducing the cost and maintaining the power quality. Again, as I mentioned, so there's definitely an outlook as to what to look for in the future. One of the things that Aconity offers is the ability to use multi-laser systems, starting with our Aconity MIDI and transitioning into the Aconity MIDI Plus, the Aconity 2. So these systems can employ multiple lasers in synchrony, right? And not only that, but the fact that you are given control through Aconity Studio to modify the parameters, modify scanning strategies, it can lead to advanced strategies that can be used for controlling the thermal input and the resultant microstructure and mechanical properties even more. So this is just an example of what those advanced scanning strategies are possible. So in here you can see we have 2 lasers that are working in synchrony. So the first one, which is the blob in the middle, is basically a laser, a regular infrared laser with a spot size of 80 microns. And then you see the supporting laser, which in this case is again the AFX ring mode, just going across. You see that it's a larger beam, right? And it provides more stability. So it is scanning in this pattern of infinity, right? Essentially creating a more stable processing region during the interaction of these 2 beams. So again, our systems have, when it comes to multi-laser systems, they have these capabilities, right? They offer through the software the manipulation of the different parameters. You can tailor, to your processing speeds, to your specific project or specific needs, whether it's for research or production. And I believe with that, I would like to thank you for your attention. Thank you, America Makes, for setting up this webinar series and inviting us to participate in this. And you have our contact information in here if you would like to get more information on our systems and the capabilities. And yeah, so thank you so much for your attention.
All right, great. Thank you, Caesar. Excuse me. Great presentation. We'll now go ahead. Excuse me. We'll head into the Q&A session. If you do have a question for Caesar and you haven't done so already, please put it in into the Q&A space on the WebEx screen, and I'll try to get to it. Let's see. We do have one here to start with. So let's see. With the productivity build, did you also adjust the power for the AFX versus the standard laser?
So I believe in this case, and let me go back to, excuse me. Only specific parameters were adjusted. I'm sure that they list those in here, but I believe, so just like they did with these, right? So they started with the baseline like this, right? So they had 700 watts of power, a specific speed, right? And then the only thing that changed between these and like the 2 emission modes were really the spot, right? But they kept consistent layer thicknesses, power, and velocity, which are like the standard parameter settings. Did that answer the question?
All right. Yes. Thank you. Great. All right. Well, I think that was the only question that we got here today. Um, if you do have other questions, you can follow up with Caesar. I think Caesar, you had your contact information there. If you want to put it up just one more time.
Definitely.
All right, great. And this presentation will be posted to the America Makes YouTube channel. So if you're interested in checking out Caesar's work again, you can go see it there or share it with any of your colleagues. So Caesar, I want to thank you again for that great presentation. That's going to wrap up today's TRX webinar series. If you have further questions, please reach out to Caesar directly. There will be a post survey going out to all those who participated. We really do appreciate the time you take to provide America Makes feedback so that we can continue to improve and strengthen the additive community. And as a reminder, if you want to be a part of the TRX webinar series, you can reach out to me, Jason Thomas.
Right. Yeah, thank you so much, Jason. And again, thank you to America Makes. And yeah, looking forward to hearing from anyone that has interest in hearing more, for sure.
All right. Thanks, Caesar.
Thank you, Jason. Bye.